Okay, hi. This is the last topic that we discussed for the semester. This closes our discussions. We're going to have a series of topics involving exponential functions. Okay, so first let's define what we mean by exponential function. Suppose that if the function is y is equal to b to the power of x, or so we say f of x is equal to b to the x. This is what we call the base of the exponential function, and x is the exponent. Okay. So now let's look what this particular function looks like in a graph. And let me give you one example. Y is equal to 2 to the x. In fact, before I do that, let me make a restriction. For instance, if in the f of x is equal to b to the x, whatever b is, b cannot equal to 1 in order to become an exponential function. Because if b is 1, then we are going to have just the horizontal line. There is no movement in the y direction. Let's also define what b implies. If b is greater than 1, the base is greater than 1, then we have exponential growth. On the other hand, if b is some number between 0 and 1, then we have exponential decay. And we use an example to justify this particular definition. And you can draw the table and verify whether this statement is true. So, let's say f of x is equal to 2 to the x. Without even drawing, we know this is an exponential growth because 2 is greater than 1. And if you do the table, x and f of x, let's start from -3, -2, -1, 0, 1, 2, and 3. Let's see what f of x would be look like. 2 to the -3 would be 1/8, right? And 2 to the -2 is 1/4. 2 to the -1 is half. 2 to the power of 0 is 1, 2 to the 1 is 2, 4, and 8. And if you transpose this into our Cartesian coordinate system, you would end up, this is 0 and 1, and then you have a graph 2 to the x. Okay. Let's justify whether a fraction describes an exponential decay. So let's do f of x is equal to half to the power of x. This is the same as saying 2 to the -x. You know about the rules of the exponents. So if we do another similar table, x and f of x, let's use the same value of x, -2, -1, 0, 1, 2, and 3. If I raise half to the power of -3, I know what I'm going to get. It would be 8. 2 to the power of -2, it is 4. and this would be 2, this is 1. Now, this would be half, and this would be 1 over 4, and this would be 1 over 8. And try to transpose this into this graph. Then you would end up with a graph that looks like this, and this is 2 to the negative x, justifying that if the base is greater than 1, we're talking about exponential growth, but if it is between 0 and 1, then it's going to be exponential decay. One other thing about exponential function. If I say y is equal to b to the x, I can have any value of y, but what? There is no number raised to some power would give us a 0. So meaning what? B to the x, there is no b to x, such that b is raising to the power of x, which gives us 0. Therefore, y cannot equal to 0. Okay? This is true for all exponential functions unless there is a shift. So, what can we say? No x-intercept. And as you can see, the graph of y is equal to 2 to the x is, you have a y-intercept, but there is no x-intercept. The same also goes when it is declining. And this is true to all exponential functions, but their transformation. We're going to talk about that also. Okay. Now, let's do some properties of the exponential function. So for instance, if I say, f of x, let's say it is 2 to the x. We have seen this in the graph. Suppose I say f of x is equal to 2 to the power of x plus 3. I'm adding 3. What does this tell me? This is the same function, the exponential function, 2 to the x, only moving what? 3 units up. So this f of x to x plus 3, this is the graph of 2 to the x shifting 3 units up. In fact, let me put another minus. So if it is minus, then it is down, 3 units up or 3 units down. Okay. So the constant number all by itself shows a vertical movement. On the other hand, if I have f of x is equal to 2 to the x plus 3, now the constant is connected with the exponent. And this is again the graph, the same graph, but this time shifting 3 units to the left. In fact, if I do minus, then I would say this is the graph of 2 to the x shifting 3 units to the right or 3 units to the left. Okay. So these are preliminary properties that we can use in describing an exponential function. And you remember we talked about a function. A function, an equation becomes a function if it is either 1 to 1, 2 to 1, or 3 to 1, meaning what? There is only one value of x. And what y is equal to b to the x, is a function, because as we have seen, the graph of b to the x is a one-to-one function. So this is a one-to-one function. We also stated, so if an equation is a function, then it must have an inverse. So the exponential function has an inverse function. Now, you remember when we were talking, replace y by x and solve for y to find the inverse function. So replace y by x is equal to b to the y. But unfortunately, we can't go any further, because now we have to find what? The exponent if x and b is given to us. But there is another way of writing x is equal to b to the y, which is the logarithm of x, b is equal to y. These are two equivalent expressions of the inverse function of the exponent, of the exponential function. Okay, so meaning what? The inverse function of exponential function is the logarithm. This is your base in the logarithm, and this is your exponent and x. And if you do the graph of the log bx or log 2x, you're gonna end up with a graph that looks, this is the logarithm of b to the x is equal to y. And mind you, the exponential function has no x-intercept. The logarithm function has no y-intercept. Okay? So, meaning what? This x cannot equal to 0. Because there is no b raised to the y which gives us a 0. Therefore, this one has no y-intercept. This one has x-intercept. And this one has y-intercept. Okay? So that is a cursory look of the exponential function and its inverse function. So in this session, what we are doing is we're going to go back and forth in solving that equation, because we use both the exponential and the logarithm to solve certain equations of exponents. Okay. So, before I do that, there is another one. Let's say this is y is equal to the x, the graph of y is equal to the x. If it increases, because this is the smallest exponential functions, because it's not the smallest integer. Let me say it could be 1.5x or 1.7x. So if you are asked to find y is equal to 3 to the x, it should be, you would end up, always it has a y-intercept as 1, and this would be 3 to the x. This time I want you to go into your calculator. I think you know about this. There is e, which is the irrational number, 2.714. It goes all the way to infinity. And in exponents, and particularly in business sectors, they use E as a profit margin. So y is equal to e to the x is some number between 2 and 3. Okay? And this is what we call the natural exponent. The inverse of this function, the natural exponent function, is y is equal to ln x. If you see ln, it refers to the inverse of e to the x. In the same way, probably you have seen it in a high school, y is equal to 10 to the x if the base is 10. So the inverse function would be log x. Without even putting 10, if we just write it this way, you know the base is 10. So here, ln, the base is e. So let's do some exercise in here. Changing the exponent into logarithm and vice versa. Now, changing from logarithmic to exponential. And once we know the formula, this is not that going to be that far. So if you have log x to the base 5 is 2, change this into the exponent function. All you need to do is what? 5 squared is equal to x, and then 25 is equal to x. So x is 25. Log b of 64 is equal to 3. And then, if you want to change this into exponent, so this would be b to the third is 64. You know b has to be 4. Okay. Log 7, 3 is y, and this is 3y to the is equal to 7, and that's writing it in this form. In that case, we can't find the value of y. We have to use a different form. Now, what about if changing from exponent to logarithm? I mean, vice versa. So we have 12 to the power of 2 is equal to x. So this is what? Log, this is your base, 12. And this is your x, it is 2. It is the same way. So 12 to the power of 2 is equal to x means log 12, base 12, x is equal to 2. b to the third is 8. Again, log b, then 8 is 3. b to the third is 8. I think that takes care of that. Now another, probably it's a universal aspect. So if I have, let's say, log 9 of 9, mind you, the base and the value of x is the same. In that instance, it is always 1. Log 20 of 20 is 1. Log 100 of 100 is 1. And log of 5, and the base could be any number, but if the value of x is 1, it's always what? The exponent has to be 0 because 5 to the 0 is 1. All right. Another rule that I'm going to ask you to think about would be, say, log b of b to the x. this is x because b to the x is equal to b to the x. If you change it into exponent, you know log b dx is x. And also another property, b of log bx is also x. B raised to the power of log bx, because log bx is what? Y. B to the y is x. So know these properties. Probably let's do one of them. So if you have log 4 and 4 raised to the power of 5 is the same as 5. And 6 log 6 of 9 is 9. Right? 6 log 6 of 9. Now we are going to write the transformation. F of x is equal to log b of x plus or minus c. This is a vertical transformation. Either it is going up, the graph is going up or down. And if you have f of x is equal to log b of x plus or minus c, so meaning what? Now the constant number is part of this. This is horizontal transformation. I think that takes care of this session.